Hello, we were discussing eigenvalue problems in the last lecture, and that was in the framework of calculus of variations. Okay. So, calculus of variations allows us to deal with free vibration problems which lead to what we call eigenvalue problems, continuous. So, we have eigenvalues and corresponding eigenfunctions. We discussed that in the context of a bar, but we can apply it for beams, plates, membranes, actually any structure. We discussed the buckling case. We will discuss that today in detail, so that we can also design a strongest column where we minimize or maximize, not minimize, maximize the buckling load, all using calculus of variations. Let us look at some of the basic equations that we call eigenvalue problems. Okay. We discussed the case of a string first, and the string problem. So, if I were to draw a string which is at both ends, it can be pinned also. There is tension T in it, that is what we consider, and that gave us the eigenvalue, that governing equation for that was this. Okay. That is the governing equation. This is the governing equation for free vibration. That is when we get an eigenvalue problem for elastic structures, and that gave us this problem which we call eigenvalue problem. Okay. From the governing equation, we saw by using the separation of variables technique how we can get this eigenvalue problem, and lambda is our eigenvalue and phi is our eigenfunction. Okay. There are many solutions, infinite solutions for that. That is what we discussed last time using framework of calculus of variations. Similar thing can be done as we have written the equations here. This one is a governing equation for an axially deforming bar, governing equation for again free vibration of a bar. So, a bar looks like this. Basically, we have written it for uniform cross section, that is why EA are outside, otherwise we would have written EAU prime and whole prime. Okay. We have a bar with, let us say, fixed and free, where its deformation is in this direction, that is U of x, and that is the free vibration again for it. If there is a bar and you pull it and it is going to vibrate, there are at different natural frequencies, again infinite natural frequencies that come about in the form of eigenvalue problem if we use this governing equation, just like we had done for a string. Okay. Now, this one over here, as you may recognize, is for a beam, transverse vibrations of a beam, free vibrations, and this one here where there is only W dot, no W double dot, it is for a beam that is under some drag. So, this is beam under drag, that is I have a musical instrument wire fixed there, and then you drag it in water, and at that time what will be its natural frequencies. That is what this equation is. The one that we will discuss today is for the column buckling. That also, this is the governing equation. We are writing only governing equations here. All these are governing equation. Just like the first one gave us the eigenvalue problem. Okay, this first one gave us the eigenvalue problem. We can get eigenvalue problems for all others. Okay, this is the column buckling, and here is one that is very general. This does not, we can get all others from this in a way, at least the second order things. This is a general eigenvalue problem, general eigenvalue problem. Okay. Basically, eigenvalue problems are characterized by a differential operator. So, there will be some differential operator acting on a function phi gives you back that function, something like this. This is a differential operators, differential operator, differential operator, okay, that transforms the phi function back to lambda times phi. All of them have this characteristic. Okay. In order to understand this and then discuss in detail the column buckling problem, not just buckling analysis, but also design. Okay. What we will do is we will get a little bit more understanding of the eigenvalue problem and buckling at the same time by taking a simple example. The example that we take is that let us imagine that there is a column, okay, and there is a compressive load P on it. So, this column has Young's modulus E, second moment of area I and length L, the usual things. No? This is Young's modulus, and this is second moment of area, and this is length. If you know these three, can you get at what load P the column will buckle? Buckling means that if the column is taken like this under the axial load, at some point it will not be able to stay vertical and just will buckle like that or like this, many other ways. When we say it is an eigenvalue problem, there are many buckling, we can call them mode shapes. Okay. We are mostly interested in the one that is fundamental buckling, that is the one that I am going to draw in over in red. This is a fundamental mode, and there will be higher modes, say second mode, third mode and so forth. There will be many or infinite buckling mode shapes. To understand this problem, this buckling problem, let us take a simpler system. Let us take actually a rigid body with a pin joint here, which is attached to some frame. Let us put a torsional spring of spring constant kappa, whose unit is going to be Newton meter per radian. Radian because we have pin joint, it can actually turn. Let us say this thing has turned like that. Okay. Let us draw a reference line here and a reference line there. Let us call this angle from here to here, let us call this theta. Okay. That it is free to rotate, we have indicated an angle. Now, let us say that there is a force there, compressive force, just like what we have over here, a P. Okay. Let us call the length of the bar L, and there is spring constant, torsion spring constant, rotational spring constant kappa, which is Newton meter per radian. As it turns, there is going to be a torque generated here. Okay. Let us take this problem and then say what happens when we start with theta equal to 0 and apply load P and then see what happens. So, we will use energy method or our principle of minimum potential energy. Let us apply the principle of minimum potential energy. Let us apply principle of uniform potential energy. Okay. When we do that, we first need to write potential energy, which is strain energy plus work potential. Strain energy is there in the form of the spring, that is half kappa theta square. Okay. Kappa theta is torque times the angle theta averaged over this thing will be this, like translational spring, if it displaces by delta and spring constant is k, half k delta square is the strain energy here, half kappa theta square, plus work potential is negative or the work done by external force. So, here we have P, which is downwards, and the P when it acts here there will be a difference between these 2 points. Okay. That is the distance we need to take. Original one, that is from here to here is L, and here to here is, this is L and this is theta, that will become L cosine theta. So, this is going to be L minus L cosine theta. Okay. So, we write that as L minus L cosine theta, then the same direction. So, that will be positive, and it is a negative of the work done. So, we will have negative. So, overall what I get for potential energy is half kappa theta square minus P into L minus L cosine theta. We know that in order for equilibrium, okay, for equilibrium, for static equilibrium, we must have dPe by d theta. Theta is our variable here, that is equal to 0. That will give us kappa into theta, half k theta square, half kappa theta square will give kappa theta when you take different derivative, and this one there is a minus, there is a minus for cosine theta, derivative cosine theta is again minus, overall it will be minus, 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 cosine the derivative minus will give us P L sin theta, that is equal to 0. Okay. So, what we get is kappa theta equal to P L sin theta, that is our static equilibrium equation. Okay. If you look back at this problem, what we have here, we see that the moment balance for this will exactly give that. If P has moved here, so when it deforms, the P is over there, right. So, that moment is P into L sin theta. L sin theta is the distance between these two, that is L sin theta. Okay. So, P L sin theta will be opposed by the torque that comes here. When it is rotated there, the torque is going to be kappa theta, and this torque. So, balance, we get the equilibrium equation. Look at this equation, and this has the nature of an eigenvalue problem. There is a differential operator, except that here it is not a differential operator, we are taking theta, applying, doing some function, getting back theta times a constant. Okay. And you can see this problem also has many solutions, and that depends on the value of k and PL. Okay. So, if I were to plot this to show theta and then kappa theta, let me do this in blue color. Okay. Kappa theta, that will be something like this. Okay. I can do both sides if I need to, right. This is kappa theta. Now, let us also do say in green color, okay, PL sin theta. Okay. It is a sin theta, regular sin theta over this color, okay, and the other side also. Okay. Now, where all they cross, obviously this point and this point and this point, we have 3 solutions here, right, where kappa theta and this other one, which is this, which is PL sin theta. Okay. Now we see that depending on the value of k, number of solution changes. If k kappa were to be very high and the curve were to be like this, okay, this is some kappa hat which is very large, larger than kappa. We have 0 as the only solution, that is a solution of this equation. As kappa decreases or p increases likewise, so more and more solutions come, right. When you had more and more solutions, whether it will be stable or unstable equilibrium will depend on the derivative of this again. So, we will write d square p e by d theta square, one more derivative will give us kappa minus p l cosine theta, this quantity. So, what we find here is that let us say theta equal to 0 is always a solution, whether it is a stable solution or not depends on the value of this second derivative. Stable means that this thing, this kappa minus p l cosine theta, cosine theta 0, if you have theta equal to 0, cosine 0 is 1. So, kappa minus p l should be greater than 0. Okay. It will be unstable equilibrium if kappa minus p l is less than 0. What will be the in between value or the critical point where it changes from stable to unstable. Okay. To begin with, when have very small p, obviously kappa minus p l will be greater than 0. As I increase p, that is when it has a chance of becoming negative and hence unstable. Okay. As I change, there will be a critical value which will be kappa equal to p l or p critical in this case is kappa by L. Okay. This kappa again Newton meter per radian and meter. So, you get the units of Newton, anyway radians does not have a unit. So, we get the force, P critical force, we get that. Okay. And of course, more and more solutions coming, that is the nature of these eigenvalue problems. Okay. But we got a critical value kappa by L for this problem. All right. So, what we do here for a column is a similar analysis where there are multiple solutions that come about, and a column such as the one that we started out today. So, this particular column, as this load increases, load is that much and that much and that much, at one critical value, okay, at one critical value, this makes this to just buckle like that, it just buckles under that load. Okay. We can use calculus variations to do what we did with minimum potential energy principle. We will do that there also, except that it will not be in one variable like we had this theta here. We will do that for the continuous function for the column. Okay. So, let us take that example. See, if I have a column, I will not show two lines, I will just show it this way. There is a load on this. Okay. If it were to buckle, let us say it is fixed and free boundary conditions. So, it has moved down something like that. Okay. We want to know how much this is, because we need that to write potential energy. We have strain energy plus work potential. Okay. Strain energy, for that we need to know when this is going, I will call it Wx. Here we are taking x like this. Normally we take horizontal per columns, we take the vertical. X is equal to 0 here, x is equal to L here, okay, length of the column. So, now strain energy, I will write it in blue. I will integrate 0 to L half E I w double prime square dx. That we know already. If there is transverse displacement w of x, what is the strain energy? I will write the work potential, okay, which again has in it strain energy, this is work potential that we have. This is the negative of the work done by external force, work done by external force. External force in this example, this problem is P, the P there. Okay. So, that since it is negative, I will put a minus sign and then P times, let us call this delta. Okay, first of all I do not need to put integral, I do not know yet, integral will come, P times delta. P times delta, negative of that is work potential. So, what is delta? Okay. This delta is, if I take a little segment there, okay, little segment, and that one which was here will be dx, that will be dx inclined. What we have is dw, what we want is this. That if I integrate for all segments, I get this delta. Okay. Let me blow it up, let me draw a larger one like that. Okay. This is dx, which was what was here, which has come here, okay, that is dx. And what is this? That is the incremental transverse displacement w. So, Pythagoras tells us that this one, if I call that dy or something, okay, what we want, that height, right, that is dx square minus dw square. Okay. Let me just write square root of dx square minus dw square. I can write this as 1 minus w prime square, take the dx out, where w prime in our notation is dw by dx. You know that this square root of 1 minus w prime square can be approximated as 1 minus w prime square by 2, approximation, when w prime is small, which is what it is, it just buckles. We are not worried about post buckling analysis, just when it buckles, small displacement, that what we get. Now, what is this delta? So, what we got is dy is the length from here till here. What do we get? This particular thing that we have, of course, dx will also be there, right. So, dx, if I integrate this, I get that, but I have to subtract from L. So, this delta that we want is the length, the total length from here till here, that is total length. From that we have to subtract this 0 to L 1 minus w prime square by 2 dx. Okay. If I do that, I get L and there is this 1, that will also be L when integrate, what minus of minus, I get 0 to L w prime square by 2 dx. Okay. With that I can write my potential energy, strain energy, which I have half E I w double prime square dx integral 0 to L. Now, I also have the same integral minus P times delta, that also comes under the integral sign, I get this, okay, dx, that is the potential energy. Using principle of minimum potential energy, we minimize that with respect to this Wx, and when you write the Euler-Lagrange equations for it, okay. So, I will write Euler-Lagrange equation for it, and for that this becomes our integrand f. So, there will be dou f by dou w minus d by dx of dou f by dou w prime plus d square by dx square of dou f by dou w double prime equal to 0, and there will be boundary conditions. Okay. That is what we have. We will write it for this. The first one anyway, that is 0 because there is no w in here, w prime is there. So, minus w prime is there, that becomes minus of minus plus, okay, dou f by dou w prime d by dx of dou f by w prime will become p. That is why minus of minus I already took care of that minus, and this minus becomes plus p into w prime, 2 and w prime square they cancel. So, that is what I get, and then plus d square by dx square into e I w double prime, that is what I get when I take derivative of that with respect to w double prime equal to 0. So, what I got now is p w, if p is constant, I take another derivative, become w double prime plus I get plus e I, if I take e and I are constant, they do not vary with x, constant area of cross section, same material throughout the beam, throughout the column, I will get this to be fourth derivative equal to 0. So, when I put w I v, I mean d, this is equal to d to the 4 w by dx to the 4, that is our notation. Okay. So, we have this. Now, this is the governing equation for the column when there is a p. Similar we had gotten for a simple bar such as this, we had gotten this equation, right, kappa theta equal to PL sin theta, and what we have here is similar, okay, PW double prime plus EI W fourth derivative equal to 0, right. Now, this equation we can get the Rayleigh quotient for it, from which we can get the buckling value and eigenvalue problem, because eigenvalue problem, if you look at it, if I take W double prime, okay, that is what I have taken here, a differential operator is being acted on it, W double prime, two derivatives you are taking, you are getting back W double prime, that is the nature of the eigenvalue problem. This is an eigenvalue problem. So, you can write the Rayleigh quotient for it. Okay. So, for that what do we do from our previous lecture? So, we multiply W double prime with W, integrate from 0 to L dx. Similarly, we do for the other one, E I W fourth derivative W dx, that will be equal to 0. All we have done is multiplied by W, we multiplied by W and integrated, that is all. If it is 0 here, it will be 0 there. Okay. Now, if we do for this one, the first term, we get the first function integral of second function, first function integral of second function 0 to L minus derivative of first function W integral of second function, that will become square dx. Okay. And now, let us do for the other one in red color, this one second term. So, that also first function which is W integral of second function, that will become triple prime 0 to L minus integral of derivative of first function integral of second function dx, that is equal to 0. One more time, we do not need to, anyway boundary conditions, this would go to 0 because the column either W or W prime will be 0. Okay. And what we are left with is 0 to L P W prime square dx, and then likewise W or W triple prime will be 0 here. The boundary conditions that you get, they will also be gone. We are left with this. Here we will do integration by parts one more time. We keep on doing until we get like a square term for Rayleigh quotient. Okay. So, if I do this integration by parts minus again first function, I will take that integral of second function 0 to L minus of minus plus 0 to L derivative of first function integral of second function, that gives us square dx equal to 0, and once again this also boundary conditions will make it go to 0. Now we get the P from the above. We can write this as 0 to L E I W double prime square dx divided by 0 to L W prime square dx. This is a Rayleigh quotient for column buckling. So, Rayleigh quotient has both numerator and denominator positive. So, it always positive. So, buckling load is positive, it cannot be negative. It is compressive already we have taken, then it is just positive. Rayleigh quotient for column buckling. Okay. Why is this important? As we said, if you take any W here, this becomes the buckling load, and this is buckling mode shape. We noted one minimum characterization theorem pertaining to eigenvalue problems in the context of Rayleigh quotient. Rayleigh quotient has this amazing property that it becomes a minimum whenever W becomes a buckling mode shape. You can take any function, okay. Let us say let us just imagine a W axis. Okay, when I say W axis, that these are functions. If I take different points, we will have different functions. They are all functions. You see, if you take that, wherever it the Rayleigh quotient for column buckling or any problem, whenever this becomes a buckling mode shape or a mode shape, then Rayleigh quotient will have a minimum there. Okay. Let us say another one over here, it will have minimum again there, another one over there, it will have minimum again there. So, everything is a minimum. So, all these points Rayleigh quotient locally becomes a minimum. That was a minimum characterization theorem that we had. Another thing, because it is a minimum, is that if I take any W hat, then I write this Rayleigh quotient for this P hat, okay, by evaluating E I W hat double prime square dx divided by 0 to L W hat prime square dx. You get a P hat value. This P hat you will find is larger than this P critical that we have, the real buckling load. In other words, whatever value you take, you will get a value that is larger than critical load. If you minimize Rayleigh quotient, okay, the Rayleigh quotient that we have there, or in this particular problem it is P critical. If you minimize this Rayleigh quotient for buckling, you get the buckling load. Using this, what we will do is we will solve a problem where we want to maximize the P critical, that will be the strongest column. We want to maximize P critical by varying, let us say, area of cross section of a column. Okay. This will give us the strongest column. If I strongest meaning it is not going to buckle. Buckling has this phrase that we buckle under pressure, right, that is you are becoming unstable. So, here when we say strongest column, that will have maximum P critical, that is what we will discuss in the next part of the talk. Thank you.